Good day and welcome back for part 2 of our discussion on how derivatives affect the shape of a graph. So a reminder from our previous video, we explored how the first derivative affects the shape of a graph. Specifically, on an interval where the first derivative is positive, the function will be increasing. On an interval where the first derivative is negative, the function will be decreasing. And then we also talked about the first derivative test, which allowed us to look at these intervals of increase and decrease to classify a critical point as being either a local maximum, a local minimum, or neither. In this video, we will shift gears to explore the second derivative, and specifically we will ask the question, what does the second derivative of a function tell us about the graph of that function? Now, intuitively, remember, a derivative represents a rate of change, so we're really asking, what is the rate of change of a rate of change? And not to spoil it for us, but it turns out that the second derivative is going to tell us something about the concavity of the graph. And hopefully you have some kind of intuitive picture of concave up versus concave down, and I'll give a definition of that to get us started, but let me just remind you graphically. To the left, we have the graph of a function which is concave up, i.e. we think it's something that's opening upward. So we think concave up. And to the right, we have the graph of a function which is opening downward, which we intuitively think of as being concave down. Now, to give a more precise definition, we will say that if the graph of a function f lies above all of its tangents on an interval, then it is called concave upward. For example, on the graph to the left, if we pick any point on the curve and we draw the tangent line, regardless of the point we choose, the curve always lies completely above those tangent lines. So in this case, the curve is called concave upward, and I will almost always abbreviate this with a simple CU, as you are more than welcome to do as well. Similarly, if the graph of f lies below all of its tangents on an interval, it's called concave downward on that interval, and I abbreviate that with a simple CD. And just to illustrate once again, if you pick any point on this right curve, when you draw the tangent line at that point, we can clearly see that the curve lies below each of its tangents. So let's go ahead and relate this specifically back to the sign of the second derivative. With the first derivative, we had the increasing-decreasing test, where the sign of the first derivative indicated where a function was increasing or decreasing. The analogous case with the second derivative is the concavity test. If the second derivative is positive on an interval, then we say the function is concave upward on that interval. Similarly, if the second derivative is negative on an interval, then we say that f is concave downward on that interval. And just to make sure we're all on the same page in terms of what we mean by concavity and how we can recognize it in the graph, there's a curve drawn below. What I would like you to do is to pause the video and just indicate to me where the curve is concave up, where the curve is concave down. And hopefully at this point you've paused the video, thought a little bit about the concavity of this curve. And just very intuitively note, we start off kind of opening downward, or you can think the curve is below all of its tangents. So that would correspond to where the curve is concave down. Then once you get right about to this point B, we kind of change the direction the curve is opening, and it's now opening upward. So we'd refer to this portion as being concave up, and then after C, we are concave down. I do want to note, though, that there are some maybe borderline or special points on this curve. So right at the point B on the curve, the point corresponding to C on the curve, at both of these points, concavity changes. That is, at B, you're going from concave down to concave up. And at C, you're going from concave up to concave down. And because of that, we refer to these points as being, I'll say IP, and that's going to indicate that it's an inflection point of the function. And just to give a definition of that, we say a point on the curve is called an inflection point of f if the function is continuous at that point and changes concavity. And from a more analytic or computational perspective, we can usually find these inflection points by determining where the second derivative is equal to 0. So typically, these occur when the second derivative is equal to 0. But with the caveat that, similar to when the first derivative is 0, that doesn't necessarily guarantee a local max and min. The same could be true with the second derivative. Let's go back to our example from the previous video. So in our previous video, we investigated the example of this fourth degree polynomial, and we determined the intervals where the function was increasing or decreasing by looking at the sign of f prime. And for this example, we will continue on by investigating the sign of f double prime to determine these intervals of concavity. So let's go ahead and differentiate and see what we end up with. So f prime x, using the power rule on each of the terms, would be 4x cubed minus 4x. F double prime x, once again using the power rule a couple times, is 12x squared minus 4. And to determine where f double prime is positive, causing the function to be concave up, or where f double prime is negative, causing the function to be concave down, we are going to look at a sign chart for f double prime. So note this is identical to our approach with f prime. So in order to determine where it's positive and negative, we first need to think about where is f double prime equal to 0, and then we'll investigate what happens in between the zeros of f double prime. So 12x squared equals 4. X squared is 1/3. So we get two values where the second derivative is equal to 0, plus or minus the square root of 1/3. Indicating those values on our number line, so we have negative the square root of 1/3, positive square root of 1/3. And what we need to do is test a single point in each of these three intervals. So to the left of minus square root of 1/3, in between those two, and then to the right of the square root of 1/3. And in the previous example, we made a somewhat elaborate table, and it turns out that we typically don't do that because it's somewhat time consuming. We just pick a single point and evaluate this function f double prime. And let me remind you from our previous example that we found the critical points of this function f. And those critical points happen to be 0 and plus or minus 1, which, note, coincidentally, 0 and plus or minus 1 would make perfectly good sample points. If we evaluate f double prime at minus 1, and remember, it's really f double prime we want to know something about, so we go back to this formula for f double prime. We would end up with 12 times minus 1 squared minus 4, which is positive. And once again, I really emphasize that we substitute into f double prime because a common mistake is making the sign chart for f double prime but going back to the original function. So it's f double prime that we substitute our sample points into. Similarly, at 0, f double prime is 12 times 0 squared minus 4, which is negative, which means that f double prime is negative on this entire interval. Similarly, f double prime of 1 is 12 times 1 squared minus 4, which is positive. And we have now determined the intervals of concavity for this function f. Wherever f double prime is positive, the function is concave upward. And similar to my observation with increasing, decreasing, I need you to write these out as explicitly as possible. So concave upward and tell me the interval. So here it would be minus infinity to minus square root 1/3. And the square root of 1/3 to infinity. And concave downward wherever f double prime is negative, which is the interval minus square root 1/3 to positive square root 1/3. And once you've determined those intervals of concavity, go ahead and circle it and make it easy for me to find, because this is going to be a smaller part of a larger problem. So to finish up our discussion on concavity, let me remind you, after we talked about these intervals of increase and decrease, there was something we called the first derivative test, which uses the first derivative to classify critical points as local maxes, mins, or neither. And it turns out we can do something very similar for the second derivative. So note, we've indicated that the function f has critical points at plus or minus 1 and 0. And a question we may want to answer is, can we classify those three critical points as local maxes, mins, or neither? Now, in this case, the information we have is where f double prime is positive, the graph of f is concave upward. Where f double prime is negative, the graph of f is concave downward. So what we can do above this number line is just give a rough indication of how the graph will behave. So when the graph is concave upward, roughly speaking, it looks something like this. And then where it's concave downward, it opens down. And note, I'm not trying to graph the function f, obviously nowhere close to it. What I'm doing is just getting a little bit of intuition. If you are concave up at a critical point of minus 1, that means it's going to have to be a local minimum. If you are concave downward at a critical point, it must correspond to a local maximum. And this intuition is exactly what the second derivative test tells us. The second derivative test is a very convenient way to classify a critical point as a local maximum or a local minimum. So if c is a critical point of our function, that is f prime c is equal to 0. And furthermore, we know the second derivative is positive at c. That is to say, we have a critical point, and the function is concave upward at that critical point. If you are concave upward at a critical point, the critical point must correspond to a local minimum. So then f has a local minimum at x equals c. Similarly, if the second derivative is negative at a critical point, that is to say the function is concave downward at a critical point, then that critical point must correspond to a local maximum. So this is a very intuitive idea if you sketch these corresponding graphs. And just to add that last statement in there, if the second derivative is negative, i.e. you're concave downward at a critical point, then f has a local maximum at x equals c. So at this point we've talked about what the first derivative and now the second derivative tells us about the shape of a graph. The next type of problem we're going to want to investigate would be combining this all together to use that information to give a rough sketch of what the graph of a function will look like. And that's where we'll pick up in our next video.